So using this, we can do a spectral decomposition of operators. So before we do that, let's introduce a nice operator, which we're going to call PI. And it's going to be the ket of psi I with the bra of psi I. So this is an outer product. Okay, so what does it do? So if I apply PI on psi I, what I get is that, so here, this is an operator. So this is where the new ket is going to be inserted. Okay, let's, we can be more precise. This is the definition of the operator, that, we basically take this bra and take the inner product with whatever we are applying it on and then multiply it by this ket. Is the definition clear?
Yes, sir.
Let's see. So if I applied on some arbitrary state, let's apply some arbitrary state phi, then it means that I get psi I times the inner product between psi I times phi. But this is a number, right? So I can move it here or anywhere. This is the definition. We can write this as, if I want, psi I phi, psi I. Okay?
Sir, can a bra act on PI? Like instead of the ket?
Yeah, it can. Yes, it can. Very good question. It can. It is implied, but yeah, it can. You can extend the definition. Yeah, that's a very good idea.
So in that case, the bra will.
Yeah.
So okay, I see. Yeah.
Yeah. Then in that case, that's a very, very nice observation. And this is the beauty of the bracket notation, is that you can do everything without the bracket notation, but the bracket notation makes all these possibilities very, very obvious. And okay, so if I apply PI on psi I, what should I get? Can someone tell me?
The same thing.
The thing itself.
What is the thing?
The ket psi I.
I should get psi I itself, right? Yeah. Now,
given that it's normalized, of course.
I think if they're normalized, yeah, okay. Because otherwise you'll get some constant. But if pi is applied on psi j, where I is not equals to j, then what will we get?
So 0.
Right.
Exactly.
Exactly. Okay. Is that clear? Why? Because let me just break it down. Pj psi p psi I. So this is going to be psi I ket, psi I bra, and then psi j. But this is orthonormal, so this is 0. So in other words, we say that pi square is equal to pi, because once you projected down, if you project it again, you won't get anything different, right? So this is also obvious. And the other thing is that if you have a projection operator pi and pj multiplying, then you will get delta ij of pi or pj. So again, these are things that you should show. From the definition that we have just given. Okay. So given the projection operator, we know that since we can express any state psi as a linear combination of this orthonormal basis psi I, that the identity operator acting on psi will give me psi, right? So it should be very easy to verify that the identity operator can be expressed as, so this goes from 1 to n, the identity operator can be expressed as the sum of all the projectors. Okay. Again, something that you want to show. If you have, if it's not obvious to you, and it's don't worry if it is not. Okay. When I first learned these things were not obvious to me. Okay. And then I'm going to end the lecture by a very nice equation. And the equation is that we know that A acting on its eigenvalue psi m gives me lambda m psi m. Then I can express A as a sum of the projectors, but each of the projectors weighted by the eigenvalue. Sorry, I keep forgetting hats, but you know what I mean. So, and this is the spectral decomposition of A. This is a very easy but very important theorem in linear algebra and quantum mechanics. Okay. So I'm going to end there. Any questions?
No, sir. Not yet.
Sir, last equation টা একটু আবার যদি
এই questionটা?
হ্যাঁ last একটা right.
So this is the, this is basically the eigenvalue equation, right? So I'm saying is that if you think of the operator, if you take this result and apply it on lambda on psi m, you will find this coming out very naturally. So this is called this is the expression expressing any Hermitian operator in terms of all the projection operators weighted by the eigenvalue of that operator. So in a matrix language, what we are saying is that this in which a matrix can be written as a diagonal matrix. Okay, that is all we are saying, right? This expression is just expressing this fact. So this is nothing very deep. Well, it's deep, but it's nothing new. You know this, but in a different language.